Okay, good afternoon, everybody. It's 12 o'clock, so we'll go ahead and get started. A couple of reminders for today, maybe just one reminder. Test 1 will be here sort of before we know it. It's about a month away. For people who get academic accommodations applied through the Blunden Center, make sure you do apply for those as soon as possible and get your test set up with them. The Blunden Center, they really get a bit swamped and they just need some lead time. So if in high school you got extra time for whatever reason, you still need to set that up here at university, and that would be through the Blunden Center. Before we get started for today, does anybody have any questions? No? Okay, looks like we're good. So last day we were still talking about waves. We talked about interference and superposition. We talked about constructive, where the waves get bigger, destructive, where they get smaller. We talked about and we showed if we have a certain condition, we can get standing waves on a string, which is a wave pattern that looks like it's standing still, even if the string is vibrating up or down. So this pre-class question is more or less like what you're doing in the lab this week. So Monday's group would have seen this morning. Thursday's group will see it on Thursday. So we're going to keep going with this idea today, and we're going to find the sets of frequencies and wavelengths that go with standing waves. So last day I did my best to see the standing waves on a slinky to make it in class. Oh, that's even worse. And then we looked at the simulation on the website from St. Mary's. I think this picture is a little better. Yeah, so this is what I've got on the slide. It's just easier to see on the screen. So we'll start by looking at these standing waves. We'll apply the boundary conditions. We'll figure out the wavelengths, and we'll figure out the frequencies, and that'll give us a way to describe standing waves on strings. So I'll switch to the slide. It's these pictures. They're just not quite as easy to see on the slide. So our very first wave that we have, remember the first wave is the simplest one. We've got nodes at either ends because we're holding the string at that point. Our simplest wave, that was the one called the fundamental. So this first wave is called the fundamental. Standing waves, sorry, typo here. Standing waves on a string. We're saying that our string has a length of L, so from here to here is a length L. That would be something you could measure, so you can find the length of a string. That's not that difficult. Also keep in mind that our analysis is for linear waves where it's a small amplitude compared to the wavelength. I've got this really exaggerated here. In fact, and you'll see this in the lab, this amplitude is not that high. It's maybe a centimeter where your wavelength is probably 15 centimeters. So just bear in mind that this is an exaggeration and we are still on linear waves. So we're going to try and figure out the wavelengths and the frequency. Let's look at our first picture with the fundamental, and let's ask what fraction of a wavelength is this? Everybody see that from the picture? This is 1/2 of a wavelength. Okay, so from node to node is 1/2 of a wavelength. So we'll label that on our picture. This is 1/2 of a wavelength. Because this is the first wavelength, I'm going to put a 1 on my symbol for lambda, showing my first wavelength. So what I see here is that 1/2 times lambda 1 is equal to the length of the string. All right, let's go to the next mode. For my next one, I ask how much of a wavelength do I have here? I go equilibrium crest, equilibrium trough, equilibrium. This is one full wavelength. So for this mode, this resonance, this harmonic, I've got the full wavelength, lambda 2, is equal to the full length of my string. Okay, we'll do one more. My next harmonic, I squeeze in another part of the wave. I ask how much of a wave is this? 1.5 or 3/2, exactly. So here's one full wavelength, there's an extra half. So my third picture, my third mode has 1 1/2 wavelengths or 3/2 wavelengths. So 3 over 2 times lambda 3 equals the length of the string. Kind of good there? We could keep going, but these first 3 pictures should be enough to get us to our general representation. So let's look at what we have in general, and I'm going to think about what is my wavelength in terms of the length of my string. So here, lambda 1 is 2 times L. Lambda 2 is L. Another way I could write that is 2L over 2. And for my third one, lambda 3 is 2L over 3. And for my top one, where I just had 2L, I could also write that as 2L over 1. So each of my wavelengths, lambda 1 is 2L, and I've got 2L over 2, 2L over 3. So here's a pattern emerging for my general condition. So in general, the standing waves will have an allowed wavelength of lambda n equals 2L divided by an integer n. We should write down when we put an n in our formula, we do have to define it. N is a set of positive integers, 1, 2, 3, dot, 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 and so on, can go on forever. This n is called the harmonic number. And it tells us essentially which mode we're in. Okay, so for this picture, if n equals 1, we're at the fundamental, and then n keeps going up. I'll give you just a little bit of caution here. I think your book does this. I sort of advise against it. I think your book says that your harmonic number is equal to the number of antinodes. In this picture, that is definitely true. If you count the antinodes, this has 1, n equals 1, that has 2 equals n equals 2, and so on. We're going to go through a whole set of geometries and a whole set of different situations. N will not always be equal to the number of antinodes, but n is equal to the mode. So you may be better off, rather than trying to remember a trick to know what n is when you look at a picture, just be able to count. So your fundamental is always the simplest, and then you keep adding a half a wavelength to go up in pictures. That will always be the same. So that behavior will always be the same. So I just caution you against using tricks to remember kind of what picture goes with what harmonic number. So there's our wavelength for standing waves on a string. We also care about the frequencies of standing waves on a string. So let's look at the frequency in each case. For my first frequency here, F1 is equal to V over lambda 1, or V over 2L, or 1V over 2L. For my next one, F2 is V over lambda 2, V over 2L over 2, 2V over 2L. My third one, F3 equals V over lambda 3, equals V over 2L over 3, equals 3V over 2L. Okay, so hopefully we can see the pattern emerging here. We've got 1, 2, and 3 times V over 2L. So in general, the frequencies for the allowed harmonics of standing waves are Fn equals n times V over 2L, again with the same n values. Okay, so n is still your harmonic number. This expression here for our Fn, we often use this. V is the square root of the tension divided by the mass per unit length. And for example, you will be using that in your lab. You'll be putting those two things together. Okay, any questions here? Yeah.
I did see another formula. It tells us Fn is equal to NV over 4N.
This one is NV over 2L.
Yeah, there was another one, NV over 4N.
Yep.
What is it used for?
We'll get there when we talk about the standing sound waves and tubes. Yep.
In the assignment, I saw something about lowest resonant frequency. Okay.
Yeah, that would be the fundamental in general. You know, you could get some twists on a question, but it just means generally the fundamental. So now I want to throw back to a question we had last day. The question we had last day was, with strings, does it always have to be a node at the ends? And the answer is yes, with a string it certainly has to be. But could we think of another example where maybe it didn't have to be? And what I grabbed from my desk was just a flexible ruler. So if I vibrate it at one end, I can make sort of a standing wave on this. You see you get a half of a wavelength from here to here. You get a little bit of a wave from here to here. This far end, where I'm not holding it, this one is actually allowed to vibrate up and down. So if you had something like this, you could have a fixed end where you're holding it and vibrating it, but the other end could actually be what we call a free end. It could be allowed to vibrate. So I'm going to ask you, maybe you could think about how could you find the set of wavelengths and frequencies on this sort of a structure. And then when we do sound waves in tubes, we're going to come back to this geometry. Okay, so this might be something you try and work on in the meantime before we come back to it. Okay, so let's take this idea, let's do an example. This example is a little bit like your lab. It's not exactly the same as your lab because you're doing that in the lab. We'll do something a little different. But it is the same kind of setup. So let's read the problem. Let's do a list as we go. Let's do a drawing as we go so we know what we're doing here. We've got a 200-gram mass hanging from a long string draped over a pulley and attached to a frequency generator. So let's put in a table. Let's put in a pulley. Let's hang the string over the pulley. We'll put a 200-gram mass on the end of the string. I'm going to call this 200-gram mass capital M just so I can work in symbols as long as I want. I'm going to attach this end of the string to the frequency generator. So this has a little metal tab which will vibrate up and down, shaking the string. This hanging mass is 200 grams. I'm going to write that in kilograms just so I don't get in trouble with my units. For this one, in the lab, you've got a fixed frequency generator. For this device, this one is variable. I can set it as low as 60 or as high as 120, so I can set the frequency on this one. So my frequency is going to be between 60 hertz and 120 hertz. And I know the mass per unit length of the string, 1.51. This is in grams. I'm going to convert to kilograms per meter. Okay, so we okay with the picture and the list of information? So, 2 parts to the question. For what frequencies between 60 and 120 can I get a standing wave on the string? Because we just showed with our equations that it's only certain frequencies. And when I find the first standing wave, and this sort of comes back to your question about the lowest allowed wave, draw that first standing wave and say what the harmonic number is. So let's get started. We're asked for a frequency, so let's write down the equation for frequencies. Fn is equal to n times v over 2L. Okay, so there's my expression for the frequency. I know that n has to be an integer, a positive integer, 1, 2, 3, and so on. Length of the string is 90 centimeters. That's given in the text of the problem. So L equals 0.9 meters. So L is okay. F I'm trying to find. That means I need my wave speed V. Okay, so to go any further, I have to figure out V. When we're doing these problems, we almost always have to use V as the square root of tension over mu. So V is the square root of the tension in the string divided by the mass per unit length. If we want to find the tension in the string, we ask why is there tension in the string? There's tension because we've hung a mass on it. So this is what makes the string tight. So this mass is what provides the tension. If we want to figure out the tension, we have to do a free body diagram. I think my handwriting's getting a little bit small, so I'm just going to zoom in a tiny bit. Okay. So the thing holding the mass up is the string, so that's the tension force. The thing pulling down on the mass is the earth, so that's the force due to gravity. So that's our mass M. Some of the forces in the y direction, put on a coordinate system. is mass times acceleration in the y. I've got my tension minus my force due to gravity is mass times acceleration. This thing doesn't go up or down, so the acceleration is equal to 0. That means the magnitude of my tension force is equal to the magnitude of the wave force equals m times g. If you start this problem and you skip right to F equals mg, you're going to lose a bunch of points because you're losing some of the physics. I'll argue that if you say F equals mg, I'm going to say that you think tension is equal to weight, but that's not true, right? They happen to have the same magnitude in this problem, and you have to show why using Newton's second law. If you're a number sort of person, you can put your numbers in, and you'll see that that's 1.962 newtons. If you're a symbol sort of person, you can leave it as mg for a while and put in your numbers at the end. Up to you, doesn't really matter. So for your tension, we can put in our numbers if we wish, or stay in symbols if we wish. If we put in our numbers, we're going to get the square root of 1.962 newtons divided by 1.51 times 10 to the minus 3 kilograms per meter. The speed of the waves on that string is 36 meters per second. So there's the speed of the waves on the string, speed of the standing waves in the waves. So there's a step we had to do in our process. Now that we know V and we know L, we can figure out what frequency of waves can exist on this string. So Fn is equal to Nv over 2L. F1 is going to be 1 times 36 meters per second divided by 2 times 0.900 meters equals 20 hertz. Now let's look at what's physically going on in this problem. Can I set my generator as low as 20 hertz? No, it doesn't go that low. So let's put an X next to this one. That's not right. For my next one, N equals 2. I'm going to back to my previous slide for a moment. So you see here, we've got our Fn equals N times V over 2L. You might notice that your fundamental frequency is V over 2L. So your N frequencies is N times your fundamental frequency. So you can use that as well. So, or Fn equals N times F1. So that's also okay to use. Because F1 is V over 2L, multiply that by N and you get the frequencies. That's a way to save yourself a little bit of math time. So if N is equal to 2, then the frequency F2 is 2 times F1 equals 40 hertz. That one's not going to work because our generator doesn't go as low as 40. If N is equal to 3, F3 is equal to 3 times F1. That one is 60 hertz. This one is going to work. Our generator can go down as far as 60 hertz. Okay, it asks us to find all of the frequencies, so let's keep going. We know we can go as high as 120. So F4, that's what we're going to get if N is equal to 4. That's 4 times F1, 80 hertz. So that one is going to work. N equals 5, F5 equals 5F1 equals 100 hertz. That one is good. N equals 6. F6 is 6F1 equals 120 hertz. That one's good. It can't go higher than 120, so we can't get any other frequencies. So we get waves for F equals 60 hertz, 80 hertz, 100 hertz, and 120 hertz. So that's what we'll get the standing waves for. Yeah?
If we just say that there's a relationship, can we just write down that we know that it's incrementing by 20, so you can just, instead of multiplying it each time?
Yeah, it's gonna be fine. Yeah, no problem. Yeah.
When you keep the values in the calculator and carry on with significant figures, it ends up in 121 at the end, so like I wouldn't put that in, so should I just round as I go to get those answers, or?
It doesn't matter.
Okay.
Yeah.
So,
If you're consistent with your workings, like if this were a test question, you were being consistent, I wouldn't dock you for that. Like, so if you got to 121 for your answer here and you said that wasn't allowed, I would agree with that answer. Yeah. So, yeah. All right, part B of our problem says sketch the first allowed standing wave and list the harmonic number. So we've already got that work done. So our first wave happens when our frequency is 60 hertz, and that was for when n equals 3. So part B, first standing wave we get, that's n equals 3 and f equals 60 hertz. So here you have to know what the n equals 3 mode looks like for a standing wave on a string. You'll probably get practiced at drawing these, or you might just remember them. So our n equals 3 mode looks like this one. So that's what that wave would look like on the string. Okay, any questions?
Shall we draw F3, F4, F5, or only one of them?
It only asks you to draw the first one. Yeah. Okay, so looks like we're good to keep going. The next page in the notes, if you had to look at them as a homework question, I won't do that one in class, but I will post the notes so that you can use that one for your studying. Now let's do sort of a conceptual question, but it can also be practical. So when the first microwave ovens came on the market, I think my family got one for the first time in like 1984 or something. When the first ones came on the market, the turntables didn't rotate. You just put the plate in and everything stayed still. Any microwave you can buy now, it always has a rotating turntable. Why? Any ideas?
To distribute.
To distribute
The heat.
what? How does it distribute the heat though? What do you mean? Okay, so you're on the right track. I'm giving you a little bit of a hard time, yep.
Does it have to do with the fact that the conduction plate is on the other side, so it's a linear wave going through, so to evenly disperse the heat, you need to rotate it, because it's only going to be a linear wave going from either right to left or left to right.
Okay, so we got waves in there, and that part is important. There's a couple of words I was kind of hoping to hear in an answer to get a waves. Pardon?
Infrared waves.
Yeah, so microwaves, but yep, they are EM waves, electromagnetic, and they're in the microwave region of EM.
Angular frequency?
Angular frequency, that'll help determine kind of what the wavelength is. So inside the microwave oven, people thinking about waves and answering waves are absolutely correct. What you get inside your microwave oven is actually a standing wave of microwaves. So if there's a standing wave, you got a node at either end, and typically, you know, going to have 1.5 wavelengths, 1 wavelength, 2 wavelengths, depends on your microwave. So this is kind of what the standing wave will look like. So if you have something in your microwave and it doesn't rotate, what do you think happens to the food that's right here at a node? At the node, it stays raw, right? Because the wave is completely canceled. What do you think happens at the antinode?
High energy. Maximum energy.
Yeah, it burns, right? That's where you get the most energy. So stuff is going to burn right here. And it's going to be raw right here. So if you put in the rotating table, it's going to rotate through the nodes and the antinodes, and it will be a more distributed heating. Even so, sometimes when you take your food out, some bits are not all even temperatures. You still have to kind of stir it up halfway through, and that's how it gets really even. So now this is a fun experiment. You can absolutely do this physics at home. If you take your microwave, you take the turntable out so that you can put a plate in that doesn't rotate, or a little shallow dish. Then if you put something in the microwave, you know, my go-to suggestion would be just a dish of scrambled eggs. If you're vegan, you might not want to use scrambled eggs. I'm sure you could use something else. So you take out the rotating, don't let it turn, put in your dish of eggs, and you let it go for a while. What you'll see is that some parts of the egg is going to be cooked, some parts are going to be raw. So you know where the nodes and antinodes are. That means you could measure the wavelength of the wave in your microwave oven. So you look at, you know, between two consecutive cooked bits is antinode to antinode. That's a half a wavelength, or two raw bits would be a half a wavelength. So you can find the wavelength. If you turn around your microwave and you look at the sticker on the back, it'll tell you what the frequency is. So then if you know the frequency and the wavelength, you can calculate the speed of the electromagnetic wave, which should be 3 times 10 to the 8. So this is some try this at home physics. You know, please give it a shot. And then if you do try it, kind of let me know how it turns out. You know, we could do a comparison. I think if you put marshmallows in, like we put Peeps in the microwave around Easter, they kind of explode. That might work too, like a dish of marshmallows. But I think those are also not vegan. I don't know what a good vegan choice is. Okay, any questions? No? Okay, so try this at home. So this is the last little bit we're going to do on this chapter before we move on to chapter 16. One last example. So in an attempt to get your name in the Guinness World Book of Records, you build a bass viol, so a big stringed instrument, with strings of length 5 meters. So this is a huge thing. From my fingertips to fingertips is about 5 feet, so it would kind of be 3 of my arms stretched end to end. One string has a linear mass density of 40 grams per meter. It's got a fundamental frequency of 20 hertz. Find the tension in the string, what's going on with the n equals 2 harmonic, and how does this relate to a sound wave in air that eventually you'll hear when you play the music. So let's see what we can tell by reading. So we're building our instrument. The strings are between fixed points. Our fixed points are nodes. So the waves that we get will look like the waves that we've been drawing and that we found our frequency and wavelength equations for. We know the length of the strings are 5 meters. We know that the linear mass density, so the mass of the string divided by the length of the string, is 0.040 kilograms per meter. And we know that the fundamental frequency is equal to 20 hertz. And then if we were thinking about what that wave looked like, we know it would look like this. You're not asked to draw it, but it's good to have that image in your head. Part A, find the tension in the string. There's only one equation really that we know to find tension. We know that V is the square root of the tension divided by the mass per unit length. That means that the tension in the string is going to be the speed squared times the mass per unit length. The mass per unit length's okay, we know that one. V we don't know just yet. We wonder if we can find it. We know that our fundamental frequency, which is 20 hertz, that's equal to V divided by 2 times L. This looks like a good way to find a speed, because we know F1, we know the length. So V is going to be F1 times 2L, 20 hertz, times 2 times 5 meters. So the speed of the wave on the string is equal to 200 meters per second. So there's our wave speed. We come back to our equation for the tension, 200 meters per second squared times 0.04 kilograms per meter. And we get that the tension in that string is 1,600 newtons. Okay, so there's part A done. Took a couple of steps, but it's not that tricky. Part B, find the frequency and the wavelength on the string if our harmonic number is 2. So for part B, I'm going to start by drawing that wave. So for my second harmonic, I know that I've got the full wave on the string. So that's got my length L, 5 meters. Lambda 2 is equal to L equals 5 meters. For our frequency, you could do n times v over 2L, or you could do n times f1. Gives you the same answer. So f2 is 2 times v over 2L, or 2 times f1 equals 40 hertz. Okay, any questions? Yeah?
Is the velocity the same if we have F1, F2?
Yes, because the velocity is determined by the tension in the string, right? So the velocity doesn't change. Good question. So now part C, that's kind of our segue into the next chapter. So we're going to start thinking about waves and sound and hearing. So let's think about what happens when the string vibrates up and down. So here's our string. It's vibrating, let's say, in its fundamental mode. The string is going up and down like this at 20 hertz, 20 oscillations per second. That string, as it vibrates up and down, hits the air molecules around it. Makes sense? The string is in the air, so it bangs into the air molecules. The string vibrates up and down 20 times per second, so it hits the air molecules 20 times per second. Make sense? So the frequency of the string is going to be equal to the frequency of the wave in air because it's being vibrated at 20 hertz. So frequency of the string equals frequency of the air equals 20 hertz. Okay? Because that's how that sound wave is going to be generated. And we're about to look kind of more closely at exactly the mechanics of how that happens. So that's the frequency, that stays the same. And then for our wavelength, the wavelength in air is going to be the speed of sound in air divided by the frequency in air. Speed of sound in air, that's a number we know or we can figure out. Typically, it's going to be about 344 meters per second divided by 20 hertz. That gives us a wavelength of 17.2 meters. Okay, so it's sort of interesting that the frequency is the same, but because the speed is so different, the wavelength is pretty different. Okay, any questions here? And as of this morning, I did open up the assignment for the next chapter, so you can get started on that whenever you're ready. So let's make our switch to chapter 16. So, the two sound waves that we study, I don't know, probably we study these more than anything else. The waves we study the most are sound waves and light waves, and we study those because that's how we get information about our world, right? Things that we hear and things that we see. So we're going to study sound waves and light waves a fair bit. What is a sound wave? It's a longitudinal wave, and a sound wave will always travel through a medium because it's a mechanical wave. And sound waves can travel through gases like air, can travel through liquids like water, that's how whales communicate, and can travel through solids. So like if you knock on a desk, you you can hear the sound travel through the desk. So sound travels through everything. We perceive the sound when the vibrations hit our eardrums. Our eardrums start to vibrate, and then brains and biology is really cool. It turns it into something our brain recognizes as sound. So people who study biology probably like that a lot. So how is sound a wave? How does that work? So let's get a sense of how that works. So cell phones out, please. Turn your volume up. Turn mine up too. Okay, this is good. We're on the right track. And then you can go to your music or whatever, ringtones, what have you. And I want you to put your hand on your phone, cover as much of your phone as you can with your hands, and hit play on your music. Okay, no judgment zone. Nobody gets to judge anybody else's music. This is an awesome sound. Okay, so could you feel it? Right? So you can feel it when you turn your music on. So what happened when you turned the music on? What was it that you felt? Once upon a time, people always had kind of big stereo systems, big speaker systems. I guess maybe some of you have that now, but maybe lots of you don't. Probably most people listen to music with their earbuds. So this is a little Bluetooth speaker that we have at home. I took the top off. If you have a speaker at home, by all means take the top off. You can have a look at it. You just pop it off with a little screwdriver. Inside is a little diaphragm. So it's plastic. Most of them are plastic. When you plug it in and you make your music, the digital signal from your phone goes to the speaker, converts it to an electronic signal, and it makes this vibrate in and out. Okay, so that's what's happening with the diaphragm. Oh no, I dented it. That's what's happening. This thing is vibrating in and out. That's happening with the speaker on your phone too. That's what you were feeling when you had your hand on top of your phone. So it was vibrating in and out. It was this diaphragm inside your phone's speaker. Okay, so that's how the mechanics of it works. Here is a FET simulation because I really like those simulations. What we've got here on this side, this is a speaker. It's going to be able to flex in and out when we turn the music on. The dots here are the air molecules. So let's look at what happens to the air molecules when we let that go. First we'll play a single tone and then we'll do a continuous tone. Woo, come back. Okay, so it flex. You see something spreading out? So you can see that traveling through. So that was a single note. And this is what happens when it keeps going. So it keeps flexing in and out. And you see waves are traveling. This looks a lot like water waves, right? It's not very different. So it's the same sort of thing that's traveling through. I'm going to hit play again. So things we notice here is that when the diaphragm flexes out, it makes the molecules squeeze together. It makes them compress. That's typically called a compression or a condensation. And I've got all these notes on the next slide. Then when the diaphragm flexes back in, it gives the air molecules some room. They spread out. That spread out bit is called a rarefaction. So they're spread out a bunch. Those compressions and rarefactions travel out through the air, so that's the motion of the air molecules, until it hits your eardrum and you perceive it as a sound. And that's why it's a longitudinal wave in air, because the vibrations are back and forth and the wave is back forward. Okay, so let's switch to our notes slide. So right here in our picture, here's the speaker with the diaphragm. Above it, I've just got an image of that longitudinal wave on the slinky that we saw in class, because we often get that as a comparison. So what happens in our first step is that the speaker pushes forward. It compresses these air molecules. That's often called a compression. Once in a while a condensation, but compression is the most common term for it. So this is a compression. If the air molecules are packed together, they're closely packed, that means it has a high pressure relative to equilibrium. So this one is high pressure. Then what happens is that these molecules bump into their neighbors, makes them compress, and that compression starts to spread forward. In the next step, the diaphragm pulls back, the air molecules have more space, they spread out. That's called a rarefaction. That's this bit. Because the air molecules have more room to spread out, they're further apart, that's a region with lower air pressure compared to equilibrium. So we see that sound waves are longitudinal waves of pressure in air. So some areas are high pressure compared to equilibrium and some are low pressure compared to equilibrium. Sound waves are sinusoidal because our electronic signals of music, they move back and forth with simple harmonic motion. That makes these a sinusoidal wave. So all of the work we've been doing with those waves apply here. When we talk about speed of sound, the speed of sound waves in air depends on the air or whatever medium it's moving through. It depends on a whack of stuff, but the thing it depends on most is temperature. Also depends, a bit on humidity. Here's our equation where it depends on temperature. So kind of going forward in problems, if you're given the room temperature, 25 degrees, 18 degrees, 30 degrees, you'd be expected to calculate the speed of sound in air. Otherwise, you might just be given the speed of sound. So the problem might say, assume the speed of sound in air is 343 meters per second. So just read for context there. Okay, any questions to here? No, all good. So we talked about speed or standing waves on strings. It turns out we can get standing waves in air columns too. So probably lots of people have done this before. If you have a water bottle or a pop bottle and you blow across it, I'm not very good at it, but I am going to try. Okay, I sort of got it, but not very well. You all can try yourself. You're better than I am at this sort of thing. If you blow across it, you should be able to get it to whistle or hum really loudly. When you get that loud sound, that's how you know you've got a standing wave in your bottle. And that's going to happen for certain wavelengths and certain frequencies. So kind of that's the next bit we're going to get to looking at, are standing waves in our column of air. So I'll go back to the computer. So this is a simulation. This one is from Penn State, I think, from Dan Russell. I've got his name here anyway. If you look up Sound Simulations Dan Russell, it'll take you to his webpage. So what this simulation is, the black dots are air molecules. You might notice that some of them are red, so you can just focus in on a couple at a time. At one end, we've got a source making a sound wave. So maybe somebody is singing, maybe he's pushing a diaphragm back and forth, who knows. The sound wave travels down the tube, it reflects off the end, and it bounces back. Under just the right conditions, you can get the pop bottle to hum, you can get the standing waves made in the air column in the tube. So that's what's happening here in this picture. Let's just put a couple of notes on our slide. So here at this side, this is going to be the vibration, or the sound source. The sound waves are going to travel down the tube with a wave speed v, about 343 meters per second. So there's our wave speed. And then sound waves are going to reflect off the fixed end. Okay, just like it reflected off the fixed end of the string and the wave bounced back. We get alternating compressions and refractions to get a standing wave in our tube. So let's start looking at how we're going to describe those. Back to our simulation. So in the simulation, the air molecules are moving back and forth. If you focus in on this bit right here, that one never ever moves, whereas this bit here moves back and forth a lot. So you can plot the displacement of those waves as a function of time. So here at the end that's vibrating, that moves up and down a lot. Right here at this bit, it never moves, that's a node. Right here it moves a lot, that's an antinode. So you can look at how the air molecules are moving, and you can plot the displacement as we go down the length of the tube. And we see that we get the nodes and the antinodes. So let's get that on our notes. So here at our open end, this is where the vibration was happening. So we had maximum motion here, that's an antinode. For some places we had no motion, that was a node. Right here at our fixed end, those air molecules are bumped right up against the end of the tube. They can't move at all because they're stuck against the end, there's nowhere to move. So this is a node as well. So where it can't move, that's a node. And where it can move a lot, that's an antinode. And then in terms of words we were using before, these are called the boundary conditions. And then the last thing we'll look at before we quit for today, we said that it was a wave in pressure. So we can ask what's going on with the pressure of these waves. So I'm back to that Dan Russell simulation again. I'll hit play. So the top one is my wave. The tube is vibrating with one end back and forth. Some places the molecules move a lot. Some places they don't move so much. So if we focus in on this red dot right here, let's look at what's happening right here. This red dot never ever moves, but sometimes the molecules squeeze close. Sometimes they spread apart. There's a lot of pressure variation right here. So sometimes it's high pressure, sometimes it's really low pressure. That corresponds to a pressure antinode. This place right here, the air molecules are moving back and forth together as a whole set. So while it moves back and forth a lot, it doesn't squish and compress. That pressure is always constant. So it's always equal to the equilibrium pressure. So a displacement antinode corresponds to a pressure node. It's equal to equilibrium pressure. Here at the end where the molecules don't move, we get a lot of variation in pressure, so an antinode down here. Okay, so that's our relationship between the displacement and the pressure. And we'll just put a couple of notes on here. So where we get no motion is our displacement node and our pressure antinode. And where we get maximum motion, we get our pressure nodes. So what you notice is that the pressure wave is exactly out of phase with the displacement wave. It's kind of exactly opposite. Okay, so we'll quit there. Today is the day I have to run to a class in another building, so I can't stick around for questions, but I do have office hours today. You're welcome to drop by this afternoon.